So what we've done so far with least squares regression or linear regression is to fit simple functions and somewhat complicated functions to data. The data could have single input, single output, or many inputs, one output, or potentially many inputs, many outputs. Um, and let's look at a few examples closer to MAE and robotics that have the flavor of fitting functions to data. Okay. Um, if you took a fluid and then subject it to a particular shear rate and measure the shear force, you might get data that looks like this. And you could fit a straight line through this data. And if you take the slope of that straight line, that's basically the viscosity of a fluid. We can imagine um, taking a piece of solid and subjecting it to tension, let's say, and um, if you apply different strains on it, it might you might subject the material to different stresses depending on the strain, and it might look like this: a linear region where the stress and the strain are linearly related, the linear elastic region, and then eventually the material may yield or potentially break, where things are a bit more nonlinear. Again, here we may fit a line here and maybe a more nonlinear function if you want to capture the whole region. Uh, maybe a cubic, but probably not a cubic. Maybe a quintic polynomial, fifth order, maybe. Okay, and we can imagine a million other things that have this flavor. Um, in aerodynamics, for instance, you might do a wind tunnel experiment where you take an object, which is maybe an airfoil, and stick it into a wind tunnel, change the velocity of the flow, change the angle of attack, maybe the orientation of the object relative to the flow, and we can measure a bunch of different things: lift, drag, maybe the whole flow field, the velocity at every point in the flow, um, temperature at various points in the flow, etc. And again, we can try to compress all this data um, into a function that approximates the relationship between this input and output, right? So imagine doing this experiment for lots of different airfoil shapes, lots of different flow velocities, lots of different angle of attacks, lots of different inputs, and then you get corresponding outputs through experiment. And then we want to find a function that relates the inputs to the outputs, right? And we could do that. Maybe some of these things are approximated reasonably by using a least squares procedure or linear least squares procedure. Maybe something else. Maybe some of these objects requires more nonlinear techniques. In robotics, you can imagine the following scenario where the input to the robot or actuator commands, the voltages that you send to the motors, maybe the torques that you ask the motors to apply. The robot's output also depends on the current robot state, like what state does the robot find itself in, what are the states of the environmental variables, like what is the state of the environment. And given these inputs, maybe the robot has certain accelerations of various parts. It might be able to do a task or not able to do the task depending on the particular input. So you can imagine doing an experiment if you had a physical robot that where you apply different actuator commands, maybe put the robot in different initial states, and maybe put the environment in different initial states, and then run the robot, collect data, and do this over and over again for lots of different inputs. And then you can fit a function that tries to approximate the relationship between the input and the output. Okay. Again, I'm not saying necessarily that this is linear regression, but the idea is that this problem can be reduced to fitting a function. So we just saw a few different examples, all of which have the same pattern. We have a system, we have a bunch of inputs, we measure or observe a bunch of different outputs. So we can imagine doing experiments or observing, collecting data, where the system is provided with different inputs, and you measure the outputs. And then once you have enough data, you can fit a function relating the inputs and outputs, right? Now, of course, if you have a large enough data set and you do a good enough job of fitting the function using some procedure, not necessarily least squares regression or linear regression, um, your function may be pretty good. Once you do that, your function may be pretty good at predicting the outputs of the system uh, for most inputs if you do a good enough job, right? This general procedure is what's called supervised learning in machine learning sort of literature, excuse me, where the you essentially follow the same procedure. What we are given or what we have are input-output pairs for lots of different inputs. So we have lots of input-output pairs, and then the goal is to fit a function that relates the input and the output. And this is basically called supervised learning. It's called supervised learning because we already know what the output is for a set of inputs. Okay, it's that aspect where it's as if the inputs are the questions you ask a system, and the outputs are the answers that that system provides, and that sort of input-output relationship contained in the data is considered to be like supervision. Okay. In any case, it's called supervised learning. Okay, so what kind of systems can we model or approximate or learn? People would use the word learn, but you can equally use the word approximate, right? With this procedure, with the supervised learning procedure. Here are a few examples. I'm going to quickly go through a few examples. Imagine the inputs are images, and the outputs are what is the object in the image or what are the objects in the image. And the function that takes these images to the objects in the image would be considered something that does image recognition, right? So how would you construct this function? You would collect data by potentially having lots and lots of people on the internet, maybe label lots of images. And then once you have this data set, you can try to fit a function. In fact, some of this labeling is done by all of us when we answer, are you a human kind of tests using reCAPTCHA, right? But people do this kind of labeling using other techniques as well, paying people to do these tasks, etc. And we'll talk a little bit about that later in the course. Where imagine doing an experiment where you have a structure, you apply some external forces, and then maybe the structure fails, maybe the structure doesn't fail. And if you have lots of different structures and lots of different levels of external forces or properties of the external forces, you collect lots of data of this flavor. And then once you have the data, you can try to find a function that relates these inputs and these outputs. And that procedure or that function will, if you do a good enough job, be able to predict failures maybe in other structures. Okay. If the input is the recorded sound of someone speaking, the output is words and sentences that they spoke, you would call that function speech recognition, essentially. So how would you construct a speech recognition software? One way to do it is to have lots of data of someone speaking, and then you have a whole bunch of people transcribe those spoken sounds. Transcribe meaning convert that into words and sentences. Like someone types out, oh, what did they say? And once you have that huge data set, you can train some function or try to learn a function that takes this as input and gives this as output, right? It's the same kind of problem. It's a function approximation problem, or you might call it a supervised learning problem or an approximation problem, a function fitting problem, whatever. They are all the same thing. Okay. How might you be able to build autonomous driving using a procedure like this? What is autonomous driving? You essentially have a destination that you want to go to, and you have various sensor data that comes from the various sensors in the car, which might include cameras and so on as well, LiDARs. Um, and maybe you have some constraints like don't hit other pedestrians and uh, don't hit other cars, avoid obstacles. In any case, all that is embedded in the sensor data in some sense, the information about uh, where other objects are in the environment. Um, so one way you could potentially imagine, I'm not saying this is a good way, but one way you can imagine building an autonomous driving uh, function, if you will, is to collect data by having lots and lots of human driving in a car and just collect all the data that the human might have access to potentially. And then the output is what the human does for steering and gas pedal. And once you have sufficient data of this flavor, you can again potentially imagine constructing a function that relates these inputs and these outputs. And that function could, in theory, if you do a good enough job of constructing the function, um, could do autonomous driving, right? At least in theory. Again, you can imagine translation, sentences in one language, sentences in another language. If you have lots of sentences in one language, lots of sentences in another language, uh, data of that flavor, if you have sufficient data of that flavor, you might actually be able to learn automatically some function that takes you from one language to another. So this I want to say is not by having lots of human driving, but having lots of translated sentences. Right? So the same sentence expressed in different languages. That's the kind of data that you would need for something like this. Okay, etc. Right? So if you want to be really grandiose, you can imagine saying the human brain, for instance, is just a system like this. If we could record human behavior in an incredible variety of circumstances, perhaps we can reverse engineer a human. Right? So people are certainly doing parts of that. For instance, each one of these things is sort of reverse engineering what a human does in a small domain of human endeavor, if you will. But you can imagine becoming more and more grand in your ambitions. Okay, so that's all I wanted to say. My point is that what we consider intelligence, quote unquote intelligence, could potentially be achieved by collecting lots and lots of data and then fitting a function between input and output. So that's the point. And all of these things, the data is often gotten actually from human intelligence, right? So humans translate someone speaking to words and sentences, and you collect sufficiently many data sets of that flavor and then build a speech recognition program. And similarly, machine translation, again, some human translates lots and lots of sentences and then use that to build an automatic translator. So it's sort of borrowed intelligence from humans. That's one caveat. Okay, so that's basically called supervised learning. All these are supervised learning tasks. They, at least at this very high level, have a similar flavor. And I just wanted to say that classically machine learning has had three flavors: supervised learning, unsupervised learning, and reinforcement learning. And we'll talk about the other things in later lectures.